So in this last discussion today, we are going to touch upon the couple of salient features of atoms' interaction with background quantum fields and inherent quantum fluctuations therein. So in the previous set of discussions, we have learned that if matter and the field are talking to each other through, say, some monopole coupling or any other coupling, what happens for any observable both from the matter sector as well as from the atomic sector, that they get changed. So the rate of change of both the sectors becomes different, and we have operators belonging to the atomic sector, raising or lowering operator, for example, they change in a particular way. The eigenstate of the operators which are corresponding to the free Hamiltonian of atom, that also changes in a particular way. While from the field sector, the ladder operator also keeps changing in a particular way, and all of them are sensitive to the coupling the atom is having with the background field. So you see, if there is no coupling, there are three important elementary results which quickly become clear to us, that the raising or lowering operator in the atomic side will just be related to their iota omega energy gap difference. The operator, which is the free Hamiltonian of the atom, would not change at all. Why it should? Because it will commute with itself if there is no coupling. There is total Hamiltonian will be that of a atom and plus that of a field, and the Hamiltonian of the atom commutes with both of them, so it will not change at all. And the atomic sector, the ladder operators will change with this term only, which is the feature of a free field theory. If the theory of the fields is compromised with a correction term in the Lagrangian, which is talking about the interaction with the atom, it will give rise to another correction term, which is the sourced correction. So all the three operators, which are rather four operators, R plus, R minus, R3 in the atomic sector, and ladder operators AK and AK dagger, which can be derived from AK, can be written in terms of their free parts and in terms of additionally there are sourced parts. So you see, free parts are without mu term. Remember, in this setting we are talking about mu times m times phi. Mu is some smallness parameter which we are keeping it handy because most of the time we are interested about linear order behavior, and in also to see what terms are sourced by interaction. So mu is just a switching function of interaction. Whenever mu is 0, there is no coupling between atom and the field. So you see, most of the source, all the source terms which is appearing Rs in plus minus operator or R3 operator, or the ladder operator of the field has this source term, all of them are necessarily a function of a mu. Mu is 0, all these source terms are 0. Okay, so therefore we can put these definitions into the equations just above, and we will get a new set of equations connecting both the free part and the source part's time evolution with whatever appears on the right hand side. Okay, so that is what we should start writing. So this also should be, by the way, there should be RF term also which I have missed. So this plus minus comes with a source term as well here, which I have missed. Anyway, so every term, for example, here R was appearing, I have written RF plus RS. Mu was appearing, I have written phi f plus phi s, and R2 similarly R plus minus here as well. So everywhere you will see whatever appears has been broken down into their free part and the source part. And we have assumed, we know that all the things which start with order mu or above, they are just the source term because they will vanish when mu goes to 0. That means if coupling turns off, whatever piece turns off, that is the source part. So that means free part is made only from mu independent terms, while mu dependent terms are all the source part. For example, if I am trying to write down for the time evolution of Rs, the source part in R plus minus, I will collect everything which depends on mu. So you see the first term over here is not function of a mu, only a Rs term is appearing over here. Okay. Now over here, if I try to write down, you will get this thing that there is a mu over here and there is a phi f, phi s, Rf, Rs, R2f, R2s, and R plus minus f and R plus minus. So what I would try to start collecting things from, so I will start collecting things from the mu dependent part only. So of course, when I had initially missed out this RF, R plus minus of S, that means in the free part there is no source term. So it should not exist as a mu independent term. So therefore, it is not written over here. Only thing, it would appear in the mu dependent part, which is here, such that if mu tends to 0, there should not be Rs. If I had put it from the beginning, then the time derivative of Rs will depend on this Rs appearing over here as well, which should not be the case, because if coupling goes down, all the terms of Rs should go down. Okay, so that means Rs time evolution, the source terms time evolution, is only controlled by this second piece over here. So if I open it up, there are 8 terms. So 2 choices, whether I choose phi f or phi s here, R2f or R2s here, and R plus f or R plus s over here. So you see 8 choices can be written. So I have written all the 8 choices. Okay. So now you see iota mu is appearing outside. And we have known that whenever Rs appears, Rs can only appear through an appearance of mu. Rs itself starts at order mu. So in all these 8 terms, there are various sort of terms. In this phi f, here I have put phi Rf, and here also I have put Rf. Then I will get the first term. In the second term, I have kept the first phi as f, second R as, the second R has become the source term, and then the third R has remained the free part. So you see one Rs has appeared. Similarly, another case would be there when I can put the second Rs over here. The second Rs over here actually. So there should be 8 terms. So first one is S, second one is F, or it could be first one is F, second one is S, or it could be both of them are S, like this. Then again, if I start with a phi s over here, so first one is F, second one is F. One source function has appeared here. Then first one is S, second one is F. Then the first one is F here, and second one is S, let's say. And lastly, both of them are S. So you see, in this term, there is no source term, only phi f, Rf, Rf appears. In this, one Rs term appears here. In this also, one Rs term appears, which is here. In this also, in this second term, 2 Rs appears. Here also only one Rs, one source function appear, which is here. In the second term, 2 source functions appear, one here and one inside the commutator. Similarly, go below, 2 source functions appear, one here and one over here. Lastly, 3 source functions appear here, here, and here. And each source function starts with order mu term. So you see the first term, which is in red, is order mu 0, and outside it gets multiplied with I mu. So overall first term is order mu. All other terms are higher order terms, either order mu square or order mu cube or order mu 4. So that means when this coupling is linear order, which is weak, I can just forget about all the green terms and only red term can be retained. That means once I have put an iota mu in the computation, all other fields can be put to their free forms, such that would be the leading order correction. That would be the leading order source correction that would be generated. So that is what we do. We write down all the interior commutators and the field appearing as their free forms, because I do not want to put a source form inside that will make the correction term second order. So I am truncating my correction up to first order in an interaction. Similarly, we have learned that if we go to the correction to any operator in the phase space of atom, this would be now talking to the Hamiltonian of the atom as well as the coupling Hamiltonian, because this also contains operators from the atomic side. So effectively, these two commutators will decide the discourse of the time evolution of any operator in the phase space of atom. As before, this can also be broken down into 2 pieces. One is the free part and one is the coupling part. And even in the coupling part, there are 2 terms which we see it can be broken into. One is coming through the vacuums flux. So one is called the vacuum fluctuation term, and another is called the self-reaction term or radiation reaction. Vacuum fluctuation term is made from the free part of the background field, and the sourced correction induced changes in the operator G, they are called the radiation reaction, because the field itself gets changed slightly because of interaction, and this gives rise to a phi of S, and that phi of S in turn decides the change in the operators sector at operators in the atomic sector. So therefore this is radiation reaction, that change in the background photonic field or any background field causes the change in the operator's rate of d tau of any operator, that is sourced by the correction term. This is radiative correction in the field, while the free part of the field also determines the change in the operator, but that is named as a vacuum fluctuation generated. This is intrinsic to the background field, while this is due to the coupling between the atom and the field, because you see phi S is itself coming because of a coupling of atom to the field, and therefore the second term, this is radiation reaction term, is a second order thing, because phi S itself is a first order effect of change. This is due to coupling. If there is no coupling, phi S will be 0. So that means it starts at order mu. So overall this term is order mu square, while in the first term everything is free part, and therefore this is order mu term. So vacuum fluctuations are slightly dominating corrections, but there is a second order correction overall which is hiding, which is radiation reaction correction to any operator. Okay. So therefore from this expression we can see that we can integrate this equation out, and we can find out what is the change in any operator due to vacuum fluctuation part and radiation reaction part, which is just the integration of these two equations. Okay, and higher order effects are ignored in this. Only the source part is written here, and inside I do not write any other higher order thing. For example, there could have been source term here as well, source term here as well, and so on. That I am not writing. Inside one source term is written, other things are their free version. Okay, so there is a truncation at the leading order. It works out in such a way that this term is order mu and this term is order mu square already, and inside that, this order mu square term inside I throw away. That means overall order mu cube term I am throwing away in this second term, and order mu square term I am throwing away in the first term. Alright. So one particular example for that could be the phase space operator, which is the atomic Hamiltonian itself, H of A. So H of A, previously we have seen it was H bar omega naught times R3, and it can again be written in terms of its free part and its sourced part. Free part is free, which as it is, it should have evolved, which it doesn't evolve at all, but there is a sourced part which is over here. Okay. Now, in the same way, if I write down the time evolution of the operator HA, then the operator HA would be changing like the general structure which we learnt about over here from these two equations. So I will put, instead of G everywhere, HA. So that will give me the rate of change in the Hamiltonian operator itself, and noting that HA itself is nothing but H bar omega times R3. So if I do that, I will get the H bar omega outside and R3 over here. Okay. So this is how I would proceed for the computation of this operator. So just let me write, there will be an extra H bar which I have missed because there was H bar already sitting in the denominator, you can see. So outside there will be H bar coming from this operator's adoption. So you can forget the H bar in the denominator for the computations. Okay. However, the structure would be like RF, R2 of F was coming, and here the space for here was to be filled by the operator G. If you remember from the slide above, the first term is R2 and whatever operator you are going to feed in. So that should be the G. That is, our case is H bar omega R3. So R3 will sit here and R3 will sit here as well at these two commutator structure. So you will get this structure R2, R3, and here also R2, R3 with phi f multiplying outside and phi f multiplying left side outside. And then there is a second order correction term which comes about, which can be written in terms of which can be written in terms of this object, which is coming from the source part, that I will write down the RS. So RS will go and sit at the first commutator and RS will go and sit at the second commutator. If I have written every H over here as RF plus R3F plus R3S. So first term is this, R3S should have been sitting inside, but recall R3S which is appearing over here, the R3S which is appearing over here, which should have appeared over here, that itself we had previously solved for equations, and R3 of S is given in terms of a commutator of free parts of the field multiplied with the commutator between RF and at one time and R2F of one time and R3F of another time. So this R3 which has appeared over here, R3 of S which has appeared over here, has been written in the integral form. So therefore one integration and mu square comes about extra, and therefore you get this structure. And previously we had discussed the free part of the field will commute with the operator side expressions, the free part of the operator side. So remember we had this confusion of operator ordering, that if there is source part that has terms belonging to both atomic side and the field side, so therefore I cannot commute them with respect to atomic side and field side operator. But free parts do commute. So therefore if you see in the first term phi f is on the left hand side, and in the second term phi f on the right is on the right hand side. Similar thing should have happened for the RS part as well. If I do for the RS part, the same thing would have happened, and then I would have got a phi s on the left and phi s on the right. That I could not have flipped, but once I write down the phi s itself in terms of its structure, the phi s which is effectively R3 of S, R3 of S can be entirely written in terms of free field operators and free field operator of the atom. So using these two things, you can say that you can combine the various phi f appearing on the right side or the left side, and they can be written in this nice anti-commutator form for the field multiplying this object. Okay. Similarly, we can write down the radiation reaction correction to the Hamiltonian itself as this expression. Put everywhere, wherever you have a G, you put roughly h bar omega times R3 here also, and do the same game again. Break R3 in terms of its free part and the source part, and for the source part, write down the expression for R3 of S like this. And this exercise yields me that the radiation reaction correction to the Hamiltonian has this nice expression. So we had seen before as well, the vacuum fluctuation has field anti-commutator and atomic operators coming in commutator form, while for radiation reaction, the fields appear in commutator and the operators belonging to atomic sector come as anti-commutator. So together, this becomes the structure for radiation reaction and vacuum fluctuation. But this is an operator of atom which becomes collectively an operator over field as well as an atom. So that means the change in the total Hamiltonian of the atomic side becomes an operator over both Hilbert spaces of the atom as well as of the field. So it should be when we try to get the numbers out, expectation values, we have to take both the states of the atom as well as the field. So let us see first, if I take the state of the field, suppose I know that the field is in the vacuum, I have not switched on, no particle in the field is excited, it is vacuum state. Then that means I have to take the expectations of this thing with the field states. So I have squeezed these operators with vacuum of the field, and you get this thing here will get squeezed with respect to the field state, and here also you will get the phi f over here and phi f over here, they will get squeezed between the field state. Now you can see only the field operators are here, these are atomic operators, they do not care about states of the field, only phi f cares about the state of the field, and then the second term anti-commutator cares about the state of the field. And in the radiation reaction, this commutator cares about the state of the field. All these operators just act on the atomic Hilbert space. Now you can see when I take the expectation with respect to the field state, the first term in the vacuum fluctuation term, that vanishes because I will get a vacuum expectation value of the field. Vacuum expectation of the free field is 0 in the vacuum state. So the first term will drop off. The vacuum fluctuations will start from the order mu square term, and you will get this expectation value of anti-commutator, which is going to be given a symbol CF, and times atomic operator's commutator. While for radiation reaction, you will see that the commutator is getting an expectation value and atomic operators are in their anti-commutative form. So you will get chi of F. Chi of F is just expectation value of anti-commutator in the vacuum state, and the atomic operators become in anti-commutator. So the rules flip. In vacuum fluctuations, the field is in anti-commutating state, in the anti-commutating order, and operators of atoms are in commutative order, while in the radiation reaction, the field is in commutative ordering, while the atomic operators are anti-commutative ordering. Anti-commutative meaning the field operators are R2 and commutator of R2 and R3, just to be sure. Now this is half our expectation in some sense, because this operator is an operator over both Hilbert space, that of field as well as that of atom. So we have just taken partial expectation with respect to the field state. Therefore, it would leave an operator as an operator over atomic Hilbert space. Therefore, this thing which is obtainable is still an operator. The field part have been put to their expectation value, but the atomic parts are just living as the operator. So they have to act on atom's state. So we can act on, let us say, the ground state of the atom and try to see what is the expectation value of in the ground state of the atom. That means how fast the Hamiltonian expectation value changes due to this coupling in the ground state of the atom. So minus, remember, was the symbol given to the ground state and plus was the symbol given to the excited state. So across the, if I take this operator, which is partial expectation with respect to field state, and take the full expectation in the ground state of the atom, I will get this D. So when I take the expectation value with respect to minus and minus here, these things will get under expectation. Even in the first term, if I take expectation with respect to minus state, these operator will get squeezed between the minus. So you see, in the first term, I will get a expectation of a commutator with respect to minus state, and in the second term, I will get expectation of an anti-commutator with respect to minus state. So ultimately, I will get a structure like the total change in the expectation value of Hamiltonian, or you can think of it as a change in the eigenvalue in the time dependent way in a loose fashion, is made up from the anti-commutator piece from the field in the vacuum getting convoluted with commutator structure of the operators from the atomic sector getting squeezed between minus state. Okay, minus is this squeezing of the commutator of R2 and this whole operator between minus. Similarly, for the radiation reaction, if I do, again the same thing will happen. It will be the first term will be the commutator now, and the second term will become anti-commutator of operators from the atomic sector, squeezed between the minus state. So this would be the change in the ground state due to vacuum fluctuation, and this will be the change in the ground state energy rather due to vacuum fluctuation, and this will be the change in the ground state energy due to radiation reaction. The same computation you can do for excited state as well, and there you will get the corresponding plus quantities. So here it should have been a plus here. So plus. So you see that the roles will almost remain the same. The first piece will not change, only the chi will now be a plus expectation, and thus in the second term C belonging to the atom will be in the plus. C is the anti-commutator, chi is the commutator. So field state remains squeezed between the vacuum in the first term, and the second term gets squeezed between the plus, that means excited state, and in the second radiation reaction driven correction, that would be just the field state in the commutator structure and the atomic state in the anti-commutator structure. In the meanwhile, this was the rate which we had previously obtained. We can integrate this equation to obtain the net change. So we remember here up to this, we had this equation, we have just integrated things out and we are obtaining the net change in the eigenvalue. Okay, this was the rate of change. You integrate it over d tau, you will get the net change. So this is how typically the change of eigenvalues of different eigenstates are obtained due to coupling of that to a field. Even though the field is in vacuum, the coupling is non-zero and quantum fluctuations appearing through the commutator and the anti-commutator. Both of these are non-zero even in the vacuum state. So commutator between the 2 points of the field which we have computed long back was, remember, 1 over delta t square minus x square. Delta x square, that was commutator. Anti-commutator has more than a subtle piece, so I will not write that over here, but both of them, even in the vacuum, are non-zero. So despite the fact that there is no particle in the field, just a coupling term is there in the Hamiltonian, all the vacuum fluctuations are able to change the eigenvalue of the hydrogen or any atom's eigenstates. So they keep changing due to vacuum fluctuation and radiation reaction. Together, the gap will also change, because previously it was gap was delta E or capital omega frequency. Now, due to radiation reaction and vacuum fluctuation, they have become slightly different. They will change in time. The integration tell you up to what time it changes to what. So ground state will change and become something over time. Excited state will change and become something over time. Ultimately, you can see, which we will not discuss in this course, but you can work it out in more detail and see that initial value they start with, ultimately over long time they will settle into a new configuration, and this will also over long time settle into a new configuration. So the gap between the excited state and the ground state does not remain the same. Initially it was delta E, and finally it becomes delta E prime after long time. Long meaning time scale longer than 1 over delta E. After long time scales, we will see they have settled into a new split difference. And that change in delta E prime and delta E is given the symbol this delta. That is the standard lamp shift in the atoms. This is happening due to vacuum fluctuations and radiation reactions only. And this is just a hallmark of quantum field, despite not present actively through any particle. No photon is present, only vacuum fluctuations are there. They are sufficient to change the hydrogen atoms or any other atoms eigen splitting. And this has been observed in lab that atoms do have this kind of lamp shift predicted value. This is not, so if I do the standard hydrogen atom computation without looking for this coupling term, then I would get some number for eigenvalue separation. But suppose hydrogen atom is talking to the background electromagnetic field through dipole coupling. I know what is the dipole expectation, meaning transition element for dipole, and I know what is the vacuum fluctuations, or that means vacuum correlators of electromagnetic field. Put together, you will get an extra correction term, which again is the order of 10 to the power minus 5 EV. So you will see that really, if you do this computation for hydrogen atom accounting for electromagnetic vacuum, you will get the eigenspace splitting between various states of atoms off by 10 to the power minus 5 EV or minus 6 EV or even minus 10 to the power 7 EV. In very sophisticated setups, this has been measured. Actual splitting in hydrogen atom is off by this much order, which is predicted by this quantum fluctuations of field. So indeed, that is a party to the determination of the splitting between eigenstates of any atom. Okay, so this is a very robust statement about the characteristics of atom which changes. Its eigenvalues and other things are not protected quantities. They change over time and ultimately settle into a vacuum allowed new separation. Theory predicts and theory gets verified in experiments as well. Okay, so this is one of the very robust predictions. Now briefly I will touch upon another aspect which is generated by vacuum fluctuation and which also nowadays is getting a traction, which is people are trying to come up with observations or experiments which can measure that, which goes by the name of witness of quantum entanglement between the atoms. I will just briefly touch it before ending the whole discussion session, and this will not be a very rigorous but only idea I will try to convey what people try to do. So the discussion of entanglement, which I am briefly going to touch upon, is pertaining to this LOCC theorem sort of thing, where you know the fact that two atoms, let us say A and B, if they are separated by space like distance, that means causal communication between them are switched off, then they cannot develop entanglement between them if initially they were entangled, if they are not talking directly through some quantum channel. Okay, if there is no quantum operator between them connecting them, then they cannot become entangled later on if initially they were disentangled. That means initially they were separable states. That is the Lossa's theorem, that unless you write an operator which acts on both of them in direct way, there is no way to generate entanglement across them. Each of them will independently evolve with their own Hamiltonian, and the states will remain separable. However, this picture gets challenged in the quantum field theoretic setup, because even if I do not actively put any operator connecting them, there is always a background field which lives in a vacuum state. So these atoms do talk to the background field through the monopole coupling or dipole coupling or spin coupling, whatever coupling which we have discussed. We will just think of as a toy example of the monopole coupling. And in background, constantly particles are being created and destroyed due to vacuum fluctuations. And due to this effect, now we can see that despite there is no active operator we have put in between A and B, but A and B both are talking to a background quantum field, a common operator which both of them are talking to, and yet if we keep the operator in the vacuum, meaning the field configuration is put in the vacuum, that means actively I do not put any quantum particles in that. Despite that, entanglement will get generated. And that is slightly, now that we have done with time evolution of Hamiltonian and other things and how the density matrix changes, now we know how to look about. So suppose initially I write down a disentangled state of the two atoms and let both of them be in their ground state. Also, let the background field be in the vacuum state. So it becomes a tripartite system. So there are three parties: the atom, the field, and the second atom. So overall, the state of the full system is ground state for the first atom, G, ground state for the second atom, and vacuum for the field. And the density matrix constructed out of it, I could write the field on the left as well. So 0, GG. So the density matrix initially for this setup would be this outer product of the state at hand. Now, if I want to write down the reduced density matrix for the atomic sector, then I will trace over the density matrix over the field configurations. That means I will trace over on the field eigen basis in some sense of complete set of states. So complete set of states I know are the Fock space elements. So I sum over this density matrix, trace over this density matrix over the Fock space of the quantum field. So when I write down this rho 0 like this NKs, ket, and the bra and the ket will undergo overlap with this ket 0 and this bra 0. So ultimately I will have terms like this or its complex conjugate. But we know since 0 also, the vacuum also is one of the element of the Fock basis, and Fock basis elements are orthonormal to each other. Therefore, it will be delta of NK and 0. It will survive only if all other modes are in vacuum. If they have any excitation, it will become overlap will become 0. So overall, the trace will only survive for one term, which is 0 here and 0 here, which will just leave things like GG, outer product GG. So both the states being ground state. So this G is depicting both the atoms are in the ground state. Let us say this will be the outer product of the reduced density matrix, and in the full basis of the reduced density matrix, there are four possibilities: both the atoms in the ground state, one atom in the ground, second in the excited, first in the excited, second in the ground, and both excited. In this space, in this basis, the density matrix is written like 1 in the upper diagonal element, and all other things are 0. So this, as you know, it's very simple pure state density matrix, which is also separable. It has 0 entanglement measure. If you know about entanglement measures, in this course we have not discussed about that, but I hope you have heard it about. From the density matrix you can constitute various entanglement measures. So this state is having trivial entanglement. It has no entanglement if you look at any operator corresponding to entanglement. Okay, whenever the states are separable, that means two atoms states, the full density matrix can be written as separable states of the two atoms, then the entanglement is 0, which is the case here. It is the direct product of G of first atom and G of the second atom. Similarly, if I would have started from GE, one atom is the ground state, another atom is in excited state, and field is in vacuum state, the same thing would have happened. Only thing, this element, for example, would have, this element GE would have turned 1 and all others would have remained 0. Okay. So this is initially, if I initially try to write things up, this is a tripartite system. All of them are independently evolving. This is evolving with field Hamiltonian. This is evolving with atomic Hamiltonian of first atom. This is evolving with the atomic Hamiltonian of the second Hamiltonian. But as soon as there is an interaction between any two of them, in this particular case, I am going to turn on interaction between the field and the first atom and the field and the second atom. But field atom first and atom second are not interacting with themselves. Then let us see what happens. In that case, I am going to write down the coupling term. The interaction Hamiltonian will be the monopole of the first atom times the field at its own location x1 and monopole at the second of the second atom and the field value at its own location, second location. So this would be the coupling term, and this, under this coupling we have to write down the change in the density matrix. It would be time evolution operator, so density matrix will evolve through some unitary, as we know. However, we also know that we can do the computation in the interaction picture as well. So I will convert every object into their interacting counterpart, which we have learnt in this course how to do by just evolving things with respect to the free part of the Hamiltonian individually. So this would be the total time evolution according to the interaction picture, where the interaction unitary is given by the only the coupling Hamiltonian, through the coupling Hamiltonian. All these things we have done. Previously we had written it as a time ordered thing. Otherwise I can just write a simple exponential from minus infinity to plus infinity without any time order. With this also you can look back at our notes in week 4, week 2 or week 3, where time dependent Hamiltonian was being discussed. Okay, so under this the first term is identity, which is trivial unitary. The second term I am going to call as order first unitary, because this is made of one interaction Hamiltonian, which will come with one single power of mu. That means it is linear order in interaction. When I write down the second order term, which is H interaction and two copies of interacting Hamiltonian, H primed, this should also be H prime, two copies of interaction Hamiltonian. That means two of such terms will go with e to the power iota h naught t and e to the power minus iota h naught t, because they have to be brought into interaction form. They will go and sit in this Hamiltonian. You can see this term will be order either mu1 square or mu2 square or mu1 mu2. So overall order mu2 square, mu square term it is. This is second order term. Similarly, there could be third order term, fourth order term. So in this discussion, I am going to stop the series at the second order, because we are going to talk about entanglement. We will see that entanglement initiates at order lambda square or order mu square. So therefore, I have to retain terms of up to order mu square if I am looking for any property of the system like entanglement, which gets generated at order mu square. Okay, I cannot just truncate it here and say that at final stage if I get order mu square term, then that is correct, because this is order mu. It will get multiplied with another order mu somewhere, which will generate order mu square term in the entanglement. But there was already this order mu square term which could have multiplied with identity to give you order mu square term as well. We will see it. Let us retain this term up to here, and then we will see why it was necessary to retain. Okay, so let us go ahead. So if I evolve this, I put this U interaction into the left and the right and put the density matrix in between. This is how the density matrix will change. It will pick up a order 1 term, which will be order mu, and order 2 term correction, which is order mu square. You can write down the whole series expansion over here on the left and its dagger on the right and start collecting terms. So I will have a identity plus identity minus all these terms on the left, and identity plus all these terms on plus in the iota term on the right hand side. And then I start doing cross multiplication. So identity times rho naught times identity will generate me the rho naught term. The first order term, where this term from left takes the rho naught and multiplies identity on the right, will give me this object u1 rho naught identity. Similarly, identity from left side rho naught and u1 from the right side, that will generate the order mu term. If I want to look at order mu square term, I will have many options possible. I can take the second order term from the left, rho naught in between, and identity of the first term or of the right term versus identity of the left unitary, rho naught in the middle, and second order correction on the of the u dagger on the right. This will give me rho naught u2 dagger. Lastly, there is another possibility that order u1 term from the left, density matrix between, and order u1 term coming from the right u dagger. So that will give you this object. So you see, this is how order by order we can compute corrections into the density matrix. So again, since we are just touching upon, I'm not going to derive all this. I'm going to just state that if you keep doing that, writing the interaction Hamiltonian, you take this and you write down the interaction Hamiltonian. By now you already know how to write down this thing. It has to be squeezed between e to the power minus I h naught t and e to the power plus I h naught t, which will be put over here. And when I try to write down the density matrix in this basis, you will get all these operators squeezed between these basis elements. So I'm just mentioning the rough structure you will get. You will get, previously I had started with only 1 over here and all other entries were 0. This time, under time evolution, these items will turn on. There are various terms which will become turned on because of these two terms which are correcting the density matrix. Okay. Initially, density matrix was just this much, which was 1 0 0 everywhere. Due to this rho 1 and rho 2, other terms have come about. All these curly I dependent terms have come from rho 1 and rho 2. Otherwise, you can see it was just 1 0 0 0 0. What are these curly i's and curly j? These are the just exponential integrals which we have learned to develop, which we have learned to compute many times during transition rates and other things. If you work out slightly carefully, write down the unitaries as the interaction picture Hamiltonian. This we have done for computing for transitions as well. So this exact operator we had written when we were writing the transition rates of atoms as well, and this as well. So all these things we have already computed, and you just look back at our notes, you will realize that all the curly I operators are very similar operators which we have already computed. So this is some version of that. Only time this you have to be careful about, it will talk about curly I a b will come about, because you see here it is unitary of 1 and unitary of 1 multiplying. Here unitary of 2 and unitary of 2, unitary of 1, unitary of 1, and plus there is overall correction term which is coming from the second order term as well. Okay. All right. So there are various possibilities which has come about. So here, okay, here also one should have u. So this is fine. This is the thing which has appeared. So overall, when I'm writing this u, this unitaries cares about a total interaction Hamiltonian, and total interaction Hamiltonian has two terms, two monopole coupling. Monopole coupling of first atom with field location at the location of first atom, and monopole of the second atom with the field at the location of the second atom. So when I write these Hamiltonians over here, correct, the interaction Hamiltonian, I have to squeeze the whole term between minus I naught free field and free operator e to the power I h naught and plus iota h naught t from this side. and that's how we will obtain the interaction Hamiltonian in the double atom system. So therefore, when I write down this U or U1 or U2, they are made up from both the atoms. So therefore, a joint property of atoms appears. Sometimes it is a double property of single atom, IAA. Sometimes it is double property of the second atom. And then there is a mixedness, AB, first atom, second atom, star, and this curly J, which are all obtainable in terms of these integrations, where the frequency, I'm writing for a general IJ. I can take value A or B. J can take a value A or B. Suppose I'm computing for curly IAB, mu A, mu B, it will become here. It will become time of the first atom, time of the second atom, frequency gap of the first atom, frequency gap of the second atom, and the separation between the first atom and second atom. This integral will be giving me curly IAB or curly IAA or curly IBB, and curly I plus, which is appearing over here in the first diagonal, that is just the difference between IAA and IBB, and curly J and curly J star, which are appearing here and here, they are also just simple integrations of the kind which we have already done. This exponential sine functions which become a delta function in long time limit, all these integrals are of very similar kind of structure. Okay, that you have to be just carefully be doing. Here only, the only fact that previously we were computing that the atom is at rest with respect to itself. So separation between two different times, we could have put it to 0. Right now it is first atom's location, which you can put to some coordinate, second atom's location. So this will become non-zero. It will not be 1. Previously for atom at rest, we had put it to 0. Now these are two atoms and their separation is finite. It is not 0. So therefore this will survive. So we have to just carefully do this integral. Otherwise this much of integration we have done so many times by now, which appears in curly J. So again, I'm briefly discussing the idea and not going for a mathematical rigor in this discussion. So you just be aware that standard monopole coupling with respect to both the atoms, even though the field is in vacuum, the density matrix changes to a more rigorous form. It is not just one element anymore. It has generated various things. And now you can see that these terms which are appearing I plus J or IAB, IAA, IBB, all these terms are made from the double coupling of mu A and mu B. So it is order mu square term. Okay, so since entanglement or the density matrix is getting corrected with order mu square term, that is why we wanted to account for all order mu square terms from the beginning. I don't want to miss any order mu square term, because ultimately the final expression I want is true up to order mu square. It is either 0 or it becomes non-zero at order mu square. So I should not miss out anything which can contribute at order mu square. So this is all this standard computations which you are welcome to try, but I just wanted to give a statement that all of them are order mu square and non-zero. All these integrals we have done so many times, so you are welcome to do it and find out how much of entanglement or at least density matrix will become this. From here you can find out with this density matrix which entanglement measure gives you what result. That discussion I am not going ahead in this set of lectures. So I'm going to end over here with this information that due to individual coupling of atoms with the background field, despite the field is in vacuum state. That means actively I can't see anything communicating between A and B, even if there is no quantum operator directly connecting them. But there is quantum fluctuations which are captured in these kind of integrals. Remember, these were coming from quantum correlations, and these exactly go and sit in the computation of the density matrix change as well. So those vacuum fluctuations generate entanglement between them. So therefore this process sets up two particles, two atoms which are initially disentangled, and there is no other active operator between them. Even after that, after some time, there is a non-trivial entanglement set up between them. Okay, so therefore vacuum state leads to development of entanglement, and this goes by the name of entanglement harvesting. Okay, so I stop over here. So I hope you had some good at least glance at vacuum properties of fields and how vacuum properties of field affect the nature of atom and properties of atom, which are very salient and new set of predictions. It is not normal day-to-day quantum mechanics, because there is a almost a hidden sector, because vacuum does not allow you to see anything directly. Only tiny fluctuations are there, which are not obviously seen by any experiment. Their indirect presence is felt by changes in things. For example, transitions are possible across ground state, spontaneous emission is possible, or the separation between the eigenstates are possible, development of entanglement is possible. So there are many avenues where this hidden sector of a quantum field affects the quantum analysis of atoms as well. So in this course, our mandate was to just have a good view of that, and I hope it was helpful in conveying that message. So we stop the course over here. Maybe in some other future course, we will discuss in more rigor what more treatment one can do with the interactions of atom and field in more observational kind of experimental kind of setup. This course was more oriented towards theoretical understanding of that. Okay, I hope you have a good, I hope you have had a good glance at these things, and it was not worthless in some sense, and it was somewhat of enjoyable to see how quantum fields are affecting the structure of atoms. Okay, so thank you for your time and attention. Of course, we stop over here, and I hope you would have a good time at exam.